Good morning, everyone. We're just gonna wait or good afternoon, sorry. We're just gonna wait a couple minutes for some more people to show up, maybe. So we're gonna be talking about some sounds and vibrations today. As we're waiting, does anyone have any favorite songs? Hi, Callie, that's a great song. It's very popular. Frozen's definitely one of my top favorite movies. Okay, just one more minute, I think, and then we'll be good to start. Yes, it is, Georgia. It's very interesting, and we're going to learn a lot today about it. All right, well, let's get started. Today, we're going to be talking about sounds and vibrations. Now, my name is Taylor. I'm with X-Chem. Welcome back to our X-Chem YouTube channel. Before we begin, I just want to give a quick thank you to our sponsors, Actua and Promo Science, for funding these opportunities. Now, what is sound really? The scientific definition of sound is vibration of molecules in air through water or any other substance. These vibrations can occur in different ranges, called frequencies. Well, what does that mean? Well, frequencies are how often vibrations occur within a specific unit of time. For example, hertz is the common measurement of frequencies. It's kind of like how centimeters measure distance. Hertz represents how many times a vibration occurs in a second. Humans can hear a range of these vibrations, but not all of them. Actually, as you can see, humans are pretty terrible at hearing high frequencies. There are many more animals that can hear many different sounds that we can't. Dogs, in fact, can hear up to 40,000 hertz, which is more than double what humans can hear. So, does anyone have any idea what these vibrations might also be known as? Any guesses you could just throw in the chat there? So Jennifer says waves. And Jen, you would be exactly right. So they're known as waves. These waves can transport energy without transporting matter. That means that they can exchange things like sound through a substance like air without actually moving the air with it. They come in two types. There are standing waves, which oscillate at a frequency that makes them appear stationary, hence standing. The wave on the left is the standing wave. Then we have traveling waves. As you can probably guess, these waves appear to travel along, like the wave on the right. Which way do they travel? Well, that's a great question. They can travel two different ways, and one is transversely. That means that the wave is traveling perpendicular to the direction that the energy is being transported. The other is longitudinally, which means that the wave is traveling parallel to the transport of energy. Sound waves travel longitudinally. Now, that's a lot of definitions and a lot of big words, so we have a quick demonstration to show for you what this all means. So I'm going to bring in my friend Caitlin with her slinky to demonstrate some waves. So first, we have our transverse wave. So transverse waves, as you can see, can travel side to side or up and down, but the energy is still being transported all the way down the slinky. Now, this is a longitudinal wave. The slinky scrunches up, and the energy travels down the wire parallel with the slinky itself. Cool, right? Thank you, Caitlin. So that was our slinky. Now that we know what sound is and how waves work, how do we hear these sounds? What about hearing? Well, our ears work as perfectly designed funnels that catch these vibrations in the air and channel them into our inner ear. They're especially good at catching human speech. Once these vibrations are caught by our outer ears, they travel down our ear canal and set up a series of even more vibrations in the middle and inner ear, which amplify the sound in our ear. In the end, they're turned into electrical signals that our auditory nerve carries to the brain to be processed as sound. It's kind of similar to how record players work. They generate a small vibration between the needle and the groove as it goes along, and that's amplified by bigger vibrations and turned into electrical signals that are played out and we hear as music. So we know what sound is, we know what waves are, and now we know how we hear them. But why do different objects make different sounds? Well, waves have different sounds depending on their nature or physical properties. How a sound wave looks and acts will change the way we hear it. We've already discussed frequency, which is how often a wave occurs per unit time, but there are many other factors that make a wave unique too, such as amplitude. Amplitude is the height of a wave from the top to the middle or the bottom to the middle. Then there's complexity, and complexity is a little harder to explain, hence why it's called complex. Essentially, complexity describes how smooth the pattern of a wave is. In real life, vibrations of sound are not perfect wave patterns. Often they're a little shakier because there are many different frequencies released by the object at the same time, and they mix together to make one big uneven wave. As you can see, sound A is very smooth because it's a perfect wave. Sound B is not as smooth. It is more complex. That's because it is a noise, and it has many different components. But how do these properties, frequency, amplitude, and complexity, change our perception of sound? Well, we hear volume, pitch, and timbre. The frequency of a wave is directly related to our interpretation of pitch. When a wave vibrates at a lower frequency, it is traveling slower in the air. As a result, we hear a lower pitch or a deeper sound. The higher the frequency, the faster the wave is traveling, and the higher pitch the noise we hear. To demonstrate, we have some beakers set up. Here are our beakers. And we have all 6 of them in a rainbow color. Each beaker has a different amount of water in it, and we have 3 different size beakers. So really, we're working with 2 different factors here. The size of the beaker and how much water is in the beaker. So how does each affect it? Does anyone have a guess on whether the sound will be a high or low pitch for the purple beaker? So Callie says low, and Georgia says low too. So let's check that out. So it sounds like the purple beaker will be making a lower sound. So what pitch do you think the little red beaker will make, high or low? If the purple beaker made a low noise, what do you think the little beaker will make? So we have a couple people saying high, and let's see if they're correct. And that's the ding, ding, ding of the correct bell, because you are right. The red beaker makes a high-pitched sound. So we can see that the sound changes the size changes the frequency of the waves. The bigger the object, the lower pitched the sound. And the smaller the object, the higher pitched the sound the object makes. But why? Well, when smaller objects vibrate with shorter waves, they will send out more waves per second than the big object will. Big objects have long waves that take longer to vibrate, meaning they're less frequent than a small object's waves, and therefore slower and lower pitched. So that's size, but what about the water? Well, let's see. The green beaker has more water than the yellow beaker. So do you think it will be higher or lower pitched than the yellow beaker? We have a couple guesses for lower. So Georgia and Rebecca think that the green beaker will make a lower noise than the yellow beaker. Let's see. And that would mean that you are all right. So the green beaker makes a lower pitched sound, and it has more water. So the more water in the beaker, the lower the frequency, it seems. It's because the water in the beaker dampens the vibrations and makes them slower than they would seem in the air. As you remember, slower vibrations means lower pitched sounds. Frequency is why a mouse's squeak is higher than a lion's roar. So let's hear the beakers one more time before we put them away. Thank you, Caitlin. So coming back to our slideshow, we can see that there's also pitch. Amplitude, on the other hand, is related to our perception of, pitch is frequency. Amplitude, on the other hand, is related to our perception of volume. So when we receive big amplitudes in our ears, they seem really loud, and small amplitudes seem really quiet. And complexity is related to our perception of timbre, or pureness of tone. The smoother the wave, the more solid or pure the sound will seem. It's the same reason why you can distinguish your friend's voice over the phone, for example. So can we see these waves? Actually, yes. Light is a wave that our eyes pick up on instead of our ears. But I know you're thinking, yeah, but what about the sound waves? Can we see sound waves? Not exactly, but we can visualize them. Using aids, we can imagine what they would look like. So we have a little experiment set up here to show one way of visualizing sound. We can put oobleck on a speaker. Now, I know you're probably thinking, what in the world is oobleck? Well, oobleck is a mixture of cornstarch and water, and it makes what we call a non-Newtonian fluid. That means that this substance is a liquid when there's no force acting upon it. But as soon as there's a force applied, it turns solid. We can use this to our advantage to show how these sounds on a speaker would seem. The sound waves push the oobleck and travel through it, turning it into more of a solid state than it was before. What we're seeing is basically the standing waves of sound moving through the oobleck and making it take these shapes. So as a warning, there's going to be some fairly loud noises, so if you're wearing headphones or anything, make sure to turn your volume down a few notches. Now, as you can see, as we play the vibration, the oobleck stands up a little. It becomes a little more solid. You can see some shapes taking form there. And then when we stop playing it, it starts to kind of liquefy and go more at rest. So let's see that one more time. All right, so that's our oobleck. Thank you once again, Caitlin. Now, that just about concludes our presentation. Is there any questions? And feel free to ask anything. I'll just wait a couple more seconds in case there might be a bit of a delay. Thank you, Georgia. Oh, my favorite song? Catch me off guard with that question. I think it's Take It Easy by Eagles, I'd have to say. Well, thank you everyone for coming out. We do live streams every Tuesday, Wednesday, Thursday at the same time, 2 p.m. Tune in tomorrow to see my friend Callie not play with fire, that's dangerous, to test some fire demonstrations. So if that's everything, I guess I'll wave goodbye for now. Thank you for coming. See you later.